Jarrett Keifer is a senior geospatial software engineer at Element 84, which is a commercial geospatial consultancy that uses open source to build effective customer solutions. His interests include education and outreach, geospatial data formats, and high performance systems and network programming. He enjoys designing systems to operate at scale, particularly to use remote sensing data and science applications, and has over 10 years of experience contributing to open source projects. Jarrett, it's a pleasure to have you here with us. Thank you for presenting. Please go ahead.
Uh, Thank you. Sorry, I started sharing and lost the mute button. Okay. It's great to be here. I'm excited to talk to you all today about this problem of object storage and what we might be able to do to solve it. Now, I realize I'm starting off with perhaps a contentious statement in saying that there's a problem with object storage. My goal here today is to convince you that there is, in fact, a problem. I do have a proposal for how we might solve it, but it's only once you agree that we have a problem that we can start to talk about a solution. So I've been on a bit of a journey over the past few months to get to this realization. I'm going to try to distill that journey down for all of you and take you along with me as concisely as possible. I'm glad Max said that 15 minutes is perhaps unreasonable because I do have more content than that. But I do want to start with a little bit of a disclaimer because I'm aware that some who have read my recent post on the Cloud Native Geo blog on this topic have felt that I've been, I don't know, a bit provocative. Uh, I just want to start by saying I'm not here to ruffle any feathers. I see what I think is a legitimate problem and I want to talk about it. I may have a specific proposal, but more than anything, I just want to have a conversation. So if I provoke anything today, I hope it's collaboration because, teamwork allows us to do greater things than we could do on our own. All right, so to dive into this, like I said, I've been on a bit of a journey. A clear sequence of events has really conspired to have me present today. It all started earlier this year at the CNG conference. My colleague Julia Signell and I were both at that conference, and we both came away with this feeling that we needed to do something to help define a better shared foundation around the principles of raster data formats. It's not just a matter of COG versus ZAR or whatever, but more that we need to have a better understanding of the fundamentals that go into data inside of a file format like compression and chunking and metadata formats and expressibility. So we started writing some blogs. And when it came to chunking, we thought we could be opinionated and provide something of a best practices guide, and that would be that. But as we got into it, it went a bit off the rails. As any of you that have seen our posts on chunking can attest, we ended up with two admittedly quite long posts. The first looking at why chunking is such a hard problem and why we struggle to find simple solutions for it. And the second diving into the history of chunking and array formats as an attempt to try to understand how we ended up with this problem. It turns out chunking is pretty important to my point, so bear with me a moment while I spend some time talking about it. So I expect most, if not all of us, are familiar with chunking, but I do want to like go back to first principles and talk about it just to make sure we're on the same page. So chunking relates to this topic of linearization. All data stored on disk, in memory, sent over the wire, whatever. Within a computer system, all data must be a one-dimensional string of bytes. So when we come with our n-dimensional data arrays or like multi-dimensional tabular data, we have to have some way to project those n-dimensional data sets down into a single dimension in order to represent them within a computer. Here are two examples. You can see how we can take two-dimensional array data and linearize it into a single dimension. The top example uses row major order. That's probably the most common form of linearization where you preserve spatial locality across rows. And then column major, it goes down columns. These are just two examples. There are other algorithms that can be used for linearization, but these are common. So chunking comes into play with linearization because when our arrays get bigger than these trivial examples, we start to use chunking as another layer of linearization within the larger linearization process to further increase spatial locality. And it's also super important for another reason. Chunks become our unit of compression and therefore our unit of data access because in order to read any part of a compressed chunk, you have to read the entire chunk to have all of the compressed data to therefore decompress it. Um, to help communicate around this complex abstract topic, I accidentally or somewhat accidentally kind of ended up vibe coding this simulator a few weeks back, and I find this to be very useful for like talking about chunking and understanding how it works a little bit better. So here we can like specify like an array and a chunk size and a query region. That then gets rendered here as our array and our chunking scheme on top of that. And we can see then how this linearizes out either with the individual cells in the array or the chunks in the array, how that would be represented on disk. And then we can look at metrics based on our query area to see how aligned our storage scheme, our chunking scheme is to our query area. So in this particular example that we're starting with, we have this 4 by 4 query area that we're requesting 16 cells. This happens to align perfectly to this chunk based on our chunking scheme. So we read one chunk that's 16 cells. We have no read amplification. Um, I created this funny index of storage alignment, one being perfect alignment, zero being impossibly unaligned, and anything in between giving you just an example of like how aligned the storage is to the query. In this case, we see this is perfect alignment. So this is great. But what happens if we change our query region a little bit and make it 5 by 5? Well, now we can see that we're actually touching four chunks. These chunks aren't contiguous in memory entirely. We have two contiguous blocks or two blocks of two contiguous chunks. And then we can see where our individual cells are that we're requesting within this file as well. Um, and how does that affect our performance here in our storage alignment? Well, we're requesting only 25 cells now, uh, and we have to read 64. And so now we're seeing that there's this read amplification coming into play. We're having to read more data than we're actually requesting to get the data that we want because, again, chunks are our unit of access, right? And we also see that we have some coalescing happening here with our reads, right? We touch four chunks, but we only have to make two reads to retrieve those four chunks. So we get some efficiency improvement here. And the storage alignment index, whatever this comes out to, is showing us that this is not particularly well aligned, at least not compared to what we had before. So how might we play with our chunking size to like increase storage alignment? Well, we started with a 4 by 4 area before and we had 4 by 4 chunks. So what if we change our chunk size to be 5 by 5 to match our new 5 by 5 query area? Does that help or does that hurt? Well, we see that we have four chunks touched again and two reads to access them. But we're actually less aligned than we were before because now our chunks are bigger and we're not on a chunk boundary, right? We're off of a chunk boundary. So we end up with even higher read amplification. This is decreasing our storage alignment. So what if we tried to, I don't know, get back to a single read, right? Let's make our chunk even bigger to just encapsulate this area that we're looking at now. And if we do that, we can like make our chunks 9 by 9. We can see we only have to read one. Our read amplification has actually gone down a little bit because now our chunk is 81 cells in size. So instead of 100 for those four chunks we had to read before, we're reading a little bit less. So our storage alignment has gone up. And we see that we only have to make one read, so that's good. But the problem with this, making our chunks even bigger, is that it's if we do have misalignment, the amplification becomes even more significant. And so in this case, it just so happens that our query area falls inside this one chunk. But if we shift it, keep it the same size, we just shift it a little bit here and move it, and now it falls on a boundary. Well, now we have to read this entire array from end to end because now we're touching all four chunks for this little bit of data that we're requesting. our read amplification has gone off the charts and our storage alignment has gone down. I could continue on with this, but for the sake of time, I'm gonna not. I'm gonna tell you, the more that I play with this chunking thing, the more that I've realized there's a seemingly simple way to address this misalignment. Use smaller chunks. If we have smaller chunks, then queries are more likely to be aligned to chunk boundaries, and those that aren't don't have to pay a massive read amplification penalty. But there is an issue with this simple suggestion. The number of read requests required to fetch chunks when they're smaller goes up and perhaps dramatically, right? Um, this we could start to see to be a problem because if there's overhead associated with each individual read request, then if we have to make many such requests at scale, then that overhead might compound into to the point that it's problematic, right? So if we start to think, well, this overhead could be large, well, then we can't have small chunks because that makes any request inefficient, unless it's like for a very small region, only touching a small number of chunks. But practically, a larger scale request is going to be inefficient just because we've used small chunks. So we start to make chunks larger. We see this pressure for larger chunks, except that larger chunks increase the possibility of misalignment. And when there is misalignment, that read amplification becomes a penalty that can make that misaligned query be impractically bad. So it's like being stuck between a rock and a hard place, right? We can improve alignment by using small chunks, but that makes the request number of requests be inefficient, or we can use large chunks, but that means that unaligned queries are impractically inefficient. Julie and I, as we wrote about this, ended up coming to this conclusion that chunks are something tyrannical. They mandate how we can access data efficiently and cause pain if we go against them. So we started asking this question of how is it that this internal storage detail has become this now front and center data access problem, not just for the highest performance computing, but also somewhat for regular users. And we started realizing it seems like we've lost something valuable here. A tooling and file formats were supposed to hide these storage details from users. So what happened? Well, among other things, object storage happened. So we should probably talk about it since this is a talk about the problem of object storage. Though first, very briefly, before I get to that, let's just talk generically about file systems for a moment. So file systems can be many things, but one simplistic view of them is as a key value store, where the keys are the file paths representing the files, and then the values are blocks in a backing block device that hold the file data. And so we map a file name to the data that it contains in a block device like a hard drive or a solid state drive. This is a basic illustration of what this could look like. We could see these files on the left here with their colors could map to then these blocks, hypothetically in this silly block device here on the right. Notably, blocks for any given file might not be contiguous, might be spread all over the block device's storage area, but that's the point of the file system is to provide this mapping of something that's user-friendly that we can identify to this range of these different blocks within the block device. Finally, let's talk about object storage. When considering the key value nature of a file system, object storage, like S3, is not really inherently different. We have a bucket now with keys, literally keys in this key value store, which are the identifiers for these objects that we're storing inside this bucket. And so these keys end up being very much like file paths in our file system, with objects being like files in the file system. The big difference here is that we don't have a single block device behind all of this storing our data. We actually have a distributed block store where our object contents are spread across potentially many different shards within this massive distributed block store. S3, for example, uses spinning hard drives for its distributed block store, like literally slow, high latency spinning drives. And it uses a huge array of these spinning drives to realize a level of performance greater than any one of those drives could do on its own. Because it's takes your data and it splits it up. It actually duplicates it using a bunch of different schemes that aren't super important, right, for this conversation. But it splits your data up across many different drives. And then when you request your data, it allows you to request it in parallel from a bunch of different sources that are all maybe slow individually, but together can deliver the data much more quickly. So let's add another object here, a pretend cog here in purple. Now, when we read a cog, at least with cloud native tooling, in cases where we don't need the entire data set, we don't end up requesting all of the bytes for the cog. Instead, as we all know, we read the cog chunk by chunk, just requesting the chunks as they're needed. That is, we fetch the metadata from that cog to build up a logical understanding of its structure. Here in this example, let's pretend it's a 6 by 6 array of chunks. And then we use that to then figure out how to make a request just for what we want. So if we only want chunk 14, we resolve what bytes those are from the cog metadata, and we make a request just for that byte range for that chunk 14. But note that the chunks for this cog are spread across the distributed block store, all across the block store. So if we want to read, let's say, 14 and 20, chunks 14 and 20, there's no reason, just like when we read a file contiguously, that we couldn't also just request those bytes in parallel from different parts of the block store to provide a response for this request for chunks 14 and 20. Except that the object model requires us to make requests against the object in its one-dimensional representation. And 14 and 20, at least in row major linearization order, will be disjoint byte ranges within this cog. And cog uses row major order, so we know we can't request 14 and 20 in a single request. We could request 14, or we could request 20. We could request 14 through 20 and have a bunch of read amplification, reading a bunch of chunks we don't actually want. But we can't request in one request 14 and 20. We have to make two requests to get that. I think there's an interesting idea here, though, that we as the client aren't actually interested in the fact that this is a cog at all. Um, what we're really after here is the logical array that it represents, right? Or perhaps even more notably, only one part of that array. So what we build up client side and client side tooling when we're using cloud native tooling here is actually this mapping or this index of the data within the cog to excuse me, the data within the cog with regard to its logical coordinates within the array, right? We want to know with array coordinates where the data is so that we can request it. But that array interface is what we present to the user. It's lower level tooling that's doing that translation from array coordinates to chunk coordinates to then the byte ranges for those chunks and then ultimately to HTTP requests to retrieve that data. So a thought here is what if instead of making this client-side tooling go through this object-based interface, this linearized interface, we instead move this chunk mapping to the server side and had something of a chunk store. I don't think it's a novel idea, but not necessarily. But before we talk more about that, I just talked a whole lot about what a client is doing to fetch data. And I think it's worth like going through that process in a little bit more detail because I'm not sure how familiar all of us are with exactly what's happening at that lower level. So let's use an extremely simplistic example here to try to all get on the same page about this. This linearized array that we saw earlier using row major order. And let's say that we want this highlighted region here, and we want to request that from our cog in object storage. So we need to be thinking about bytes. So let's rewrite those values in a byte format for a hypothetical cog. This is all very much simplified as an example, but the principle still applies, right? So what we're doing here is we're identifying a single multi-dimensional slice, or maybe I should say a one-dimensional slice across two dimensions in our data set that we're interested in reading here. And then just as we had to linearize our data values for storage, taking our multi-dimensional array and linearizing it for storage, we too need to linearize our slice for this querying. So in the simple example, we see we end up with two one-dimensional slices within our linearized bytes. And to fetch these, we have to make two HTTP requests, one for each of those two ranges. A couple notes here. Uh, the slices, this is in Python notation with an exclusive end coordinate, whereas the range header in HTTP requests uses an inclusive end. So these are equivalent, even if they look a little different. And also, perhaps more importantly, realistically, what we would be doing here is reading chunks, right? Again, this is a simplistic example, but the process here remains the same. We identify what region we're interested in. We then resolve what byte ranges represent that in our object, and then we figure out how many requests we have to make for those different byte ranges, and we make them. I want to contrast this process to that of reading data from a ZAR, or I guess specifically an unsharded ZAR. Because I think there's something interesting to be gleaned from this case as well. So ZAR is different than traditional raster formats like a TIFF or a cog based on a TIFF. Um, each chunk is stored in a separate file. So in a traditional fi raster file where we take the values in a particular chunk and we linearize those, and then we linearize all of our chunks together and write that whole stream out to a file. ZAR linearizes the chunks and then it writes each of those to an individual file or an individual object in object storage. So if we go back to our object storage example of our cog before and replace this with a corresponding ZAR, unsharded ZAR, we could end up with something like this, where those chunks that were previously part of a single object are now individual objects in the object store. Note that these objects themselves will be spread across multiple shards and duplicated and distributed across the block store, but that's not super important to the example. The important point here is to note that we can't coalesce reads anymore. In the cog, where we might have had like 14 through 20, we could have made one single range read for all those chunks 14 through 20, right? If we wanted to do that here in this uncharted ZAR, we have to make the individual requests for each of those chunks, 14 through 20. But there's an advantage here. And the reason I walk through this example is to see that clients don't have to think about bytes in this, right? That previous process of figuring out what chunks to request and then what byte ranges those are, we stop after the first step and we just start making requests. So we figure out we want these chunks, let's request them. Implicitly, we're using object storage here as the mapping of those chunks to their byte ranges. We push that responsibility to the server side with the trade-off that we can't coalesce chunk reads, but we are seeing like shifting this responsibility from client-side tooling to the server side with this unsharded ZAR example. And I think that's interesting with this chunk store idea. The thing is, object stores are really a quite amazing technology. It's like truly foundational technology. Don't hear me saying otherwise. Um, the only real issue with object stores comes from the imposition of this object model on our multi-dimensional data access. That is, objects erroneously impose this linear byte space interface. I think it's worth asking the question, do we even need objects for data access? I'm not sure that we do. It shouldn't matter how the chunks are arranged within objects in this distributed block store. We could ditch this object-based API for multi-dimensional dataset access if we have that API side maintain the mapping of coordinate dimensions to chunk bytes, right? That mapping, that indexing that we're building up on the client side today, if we just move that to the server side, clients can then make a request using slices, any slice that they want, which then would resolve whatever chunks are required to fulfill that request, just grabbing in parallel from this distributed block store, the same way that is done when you request from an object, just not limited to that object's one-dimensional bytes interface. And a key point to this is if we're using coordinate dimensions or slices for these requests, uh, we can fulfill that with any number of chunks. It could be one chunk, it could be 100 chunks. it doesn't really matter. We can fulfill the logical request with whatever it takes. And that frees us up to now start making our chunks smaller because we are decoupling the users requesting a certain area from the number of chunks it takes to fulfill that request, right? We can use smaller chunks without then incurring this massive number of requests, this explosion of requests to fulfill what a user is then asking for. And I think it's important to note here that object store design already gets us most of the way to this. It's really only this API edge where we end up with this problem because there's no alternate way today to get access to the chunks in a manner disconnected from this one-dimensional linear byte range concept of the object. We see this push chunk sizes larger, and then we end up with arguments about chunk sizes, and chunk alignment. And this to me is the problem of object storage, the problem that the object model imposes on multidimensional data access. So I want to pause because I know that was a lot. Like I said, I do have a proposal for how we might solve this problem of object storage, but I want to pause before I get into that to open it up for questions, comments. Let's discuss because I think, this could be a controversial idea. What do people think? Yeah, yeah. So here's my proposal. It's something I'm calling the Coalesced Chunk Retrieval Protocol, or CCRP. Now, note that this is still just a proposal. I haven't yet implemented anything. The examples are admittedly a little bit hand wavy, but I think they do a good job of demonstrating the concepts that I have in mind here. So this is an example of a request. Notice that we're not using bytes in this request. We're not even using chunks per se. We're simply making a request with our slice in our dataset's coordinate dimensions. And this will return however many chunks that this request maps to. Now, this might look familiar, like that tiled thing I'm not particularly familiar with, but I know this has been compared to OpenDAP by some, or I heard web coverage service. It looked somewhat like that. So, this could look like any number of things that already exist. I think the difference here with what I'm proposing is that this is not a compute engine, does not want to be a compute engine. That is an anti-goal, being like doing any sort of compute on this. This should just be a bytes broker. It does the coordinate to chunk resolution to resolve what chunks are actually touched by user's query and returns those untouched. It doesn't do resampling, subsetting, or any sort of transformation. It doesn't decompress chunks. It returns the same exact bytes that a client would otherwise get back via multiple requests to object store via an object store API today. It's just doing it in a way that we can make one request to get multiple chunks back that are disconnected from coalescing uh, within a specific one-dimensional byte range. I also kind of like to think of this as maybe this is a silly way to phrase this, but predicate push down in an API. I've used a lot of array examples so far, but I think this applies to other types of data, like Parquet files, tabular data. They are chunked as well. Um, we can use the same sort of indexing. It's a slightly different form of indexing, but it's still conceptually very similar. If we look at like what DuckDB does, or Spark to fetch data from a Parquet file, it goes and fetches a bunch of metadata that gives it an understanding of what data chunks exist within that file, and enough context to know what chunks that are going to need to be fetched to fulfill a user's query. So a user types in a SQL query, they put a bunch of predicates in it. It then uses those predicates and the statistics of the chunks to figure out what to fetch. We can build up that same exact index these client-side tools are doing for Parquet or other tabular data formats in the same way to facilitate more efficient retrieval of chunk data, not just array data, but also tabular format data. Any multi-dimensional data this that's been chunked, this should be a viable API for. Uh, I'm envisioning CCRP to use multi-part responses to return chunk data. This allows us to, along with a binary blob for a chunk, include some sort of identifying information so the client can then reassemble that on its side when it receives those chunks. And this also decouples the API from any particular ordering within the response, allowing the API to just to return chunks as soon as it gets it from the backing block store in whatever order that is. So the client and the server don't have to negotiate some sort of order beforehand. This is the extent of the API as I'm currently proposing. The main points here are that there's a dataset endpoint you can use to list available datasets. That's sort of like listing objects in a bucket, but at this more logical dataset level instead of the individual object level. Um, there is then the specific dataset endpoint where you can fetch metadata for a specific dataset that would give the client everything it needs to know what that dataset is and how to use the data, similarly to what we already do today to fetch metadata from a portion of a cloud native file using a range read. You just hit this one endpoint to get it, or in the ZAR case, reading the ZAR metadata object. And then there are two data endpoints down here, or one endpoint with two methods, I should say. Uh, Get is obviously to retrieve the bytes for a given query, a given request. The head method could be used to plan a query so that you could see, oh, if I make this request, it's going to be a gigabyte response and size. And this actually allows um, one point here is I keep saying let's make one request to get any number of chunks that we want, but uh, that's not always the most performant way to download a massive amount of data. You might want to use multiple download streams to fully saturate a connection. But these are two conflicting or two concerns that we can decouple, right? First is how big is the response going to be for a given query. The second is, oh, it's going to be this big. Let me split that up into 100 megabytes at a time and download that across parallel workers, something like that. CCRP doesn't force you into making having to download a massive amount of data via a single connection. It's just saying that you could make one request to get any number of chunks. So let's decouple the number of chunks from the number of requests from how you actually want to do performant downloading. This is an example of what the metadata for a data set might look like. It's right now really just a minimal wrapper around a native metadata format. Like in this case, ZAR, you would embed the ZAR metadata for an array in here. Uh, I'm really excited about this though, because I feel like there's a lot of potential with like having the ability to specify more things around just the data set's metadata. Like the idea of links here, being able to link to related data sets. I think this could allow us to do a lot of deduplication if we have coordinate arrays, for example, that are duplicated across many groups. We could just have one central coordinate array and have a bunch of things linked to that. Say, this is my coordinate array, go fetch it from there. Um, and option like I'm envisioning this tie-in with Iceberg and Ice Chunk to be able to have the ability to facilitate versioning, um, and be able to advertise like what the latest version is or tie requests to specific versions for reproducibility. If you're trying to request the same data you fetched last month and the data set's been updated, well, if that version is still around, you should be able to specify that version when you make your request again if you need the data again. Now, I've published a rough draft of this spec at ccrp.dev. This is a very rough draft. Beware of that. The intent of this is a starting point for discussion. There are pieces of this that are like the examples, for example, as an example, the examples are LLM generated and need to be heavily revised. They're pretty bad in some cases. But the high level pieces I think are all there and are a starting point for discussion. I really put a lot of time into like the protocol flows and the implementation considerations and facts pages. But even the API reference is a pretty good sketch of what I'm proposing that we can use as a starting point to talk about this. And the query syntax as well is, I think, fairly well there. Like this is a starting point we can iterate on. And to that end, all of this is open source. Anyone can contribute. You can go to the GitHub page open issues, open pull requests, start a discussion, tell me how much you hate or love this idea. I'm happy to engage with whatever there. I just hope that we can get some excitement and interest around this idea, enough that we could put together a sprint to come together to work on this, see if we can set enough direction to start a proof of concept implementation, to show that this is a viable and powerful idea that could help get around this problem of object storage, this problem of this one-dimensional interface that we have to use to access multidimensional data, and ultimately allow for smaller chunks and usurp this tyranny that is posed upon us. So thanks for everyone for sticking with me. That's all I've got. Happy to take the rest of the time to talk about this or answer any more questions.